Okay, so welcome everyone to the Hope Science Journey webinar. My name is Mozart Sharif. I'm the Science Initiatives Coordinator under the Emirates Mars Mission. So I hope everyone is doing good. This is the last series of the Hope Science Journey webinar, where we will have a series of interesting presentations from the team. These are the list of presentations we will have for today. We will have first the thermophysical properties of Mars, then we will move to the EMERS data simulator and EMERS footprint mapping. Then we will move to the dust storm effects on water vapor and hydrogen on Mars, and then the forward modeling of oxygen on Mars, and the oxygen in response to solar activities and water on Mars. So these are the list of presentations we will be having for this session. So it's not as in, if you've been here in the previous sessions, it's not an introductory session. We will just dive in deeper into the sciences, hence the name of the webinar. So this session will be from 4 to 6 p.m. And if anyone does have any questions, please leave them in the in the Q&A box, and the team will be happy to respond to you with a typed response or live by the end of the session. We did have a few people that tend to raise their hands throughout the sessions, but or just send in their questions in the chat box. We will only be referring to the questions in the Q&A box. So whatever questions that you might be having, please leave them in the Q&A box. And in the future, if you would like to stay connected with us and to know more about the future events, webinars, or latest news, please feel free to take a screenshot or take a picture of this slide right here, which has all the social media platforms of the Mohammed bin Rashid Space Center and the Hope Mars mission as well. So I'll just leave it up for the next 30 seconds for everyone to take just a screenshot of that. And without further ado, we will start off with Noura Al-Meheri's presentation on the thermophysical properties of Mars. Noura, please, you may go ahead.
Thank you, Moza. I'm gonna share my screen. Let me know if you can see it.
Yes.
So yeah. Hi everyone, my name is Noura Al-Meheri. I'm a science data analyst in the Emirates Mars mission. My project is about thermophysical properties of Mars, so I'm gonna present the project to you. This is the outline for the presentation for today, and it is the methodology that I've been followed to accomplish my project, starting with project alignment with Emirates Mars mission, literature review, selecting study regions, as well as conducting few analysis. So the objective of this project is basically to explore the sensitivity of the Martian atmosphere on derived surface properties such as thermal inertia and albedo using a thermal model in JMARS. JMARS is a visualization tool. So in order to reproduce a systematic set of observed surface temperatures that are done for different set of atmospheric scenarios. So the ultimate goal of this project is basically to undertake the study using the Emirates Mars mission two instruments, which are EXI, Emirates Exploration Imager, as well as EMERS, which is Emirates Infrared Spectrometer, in order to understand the atmospheric variability, as well as taking the diurnal observations that these instruments will be providing. But however, for this project, I'm gonna use the instruments data sets that are from Mars Global Surveyor, which are Mars Observers Camera MOC, as well as a thermal emission spectrometer test as a proxies for EMERS and AXI instruments. So for that, I'm developing my skills in thermal modeling and data analysis and visualization, all in which it will feed the EMM's objective one, which is characterizing the state of Martian lower atmosphere. Here you can see the radiation budget of the Martian atmosphere. Radiation budget meaning the basically it represents the balance between the incoming solar radiation as well as the outgoing radiation. And it could be mainly solar radiation or any radiation emitted by the Martian system, including the atmosphere. So any thermophysical properties could induce a change in radiation budget of the Martian atmosphere if they changed. So what are thermophysical properties? So basically thermophysical properties are properties of a material that are induced if heat was applied. Such a property includes thermal expansion of a material as well as thermal stress that is result of thermal expansion. And then we have thermal inertia, which is basically the ability of a material to store energy during the daytime and to radiate it back at during the nighttime. And in order to calculate the thermal inertia of a material, we need to know the material's density and its specific capacity as well as its conductivity. Other than that, we have albedo as a thermophysical property, which is a fraction of light that is being reflected off a body or a surface. All of these thermophysical properties are known to play an important role in the radiation budget of the Martian atmosphere. So let's look into deeply into the thermal inertia, and then we will focus on the albedo. So thermal inertia is a measure of material responses to changes in temperature, and it's the ability of a material to store heat during the day and then radiate it back at night. So thermal inertia is basically used to characterize the surface properties. So let's say if we have a material that is classified as a rocky and exposed bedrock or consolidated data or consolidated material, it induces a higher value of thermal inertia. And typically it's considered as a dark area. On the other hand, if we have any surface materials that are classified as a grain or loosely packed surface material, they usually tend to exhibit low value of thermal inertia, and they are typically known as a bright area. So let's look into these infographics that we have in the here, just to understand thermal inertia variation in two different scenarios. So we have two scenarios, which is during the day and at night. And we can see yellow arrow, it's basically the light is being coming from the energy source, and the orange arrow is basically the heat or energy is being reflected back from the surface to the atmosphere. So if we look into the sand, on the left image. So sand is considered as a fine-grained, loosely packed surface material. So sand during the day heats up very quickly, and as a result, it radiates more energy or heat to the atmosphere. On the other hand, at night, sand produces or emits less energy to the atmosphere. And then if we look at the concrete is considered as a tightly packed material. So during the day, it takes more time to just heat up. And therefore, it's cold to the touch during the day, and it radiates less heat. However, at night, it radiates more heat, and because of that, it's warm to the touch. Moving into the albedo. Albedo is basically the amount of light reflected from planet's surface, and it plays an important role in varying the temperature. It's basically looking into how much energy is being reflected rather than how much energy is being absorbed. So let's see if we have a light colored surfaces, a bright region. So bright regions, they do not tend to absorb energy as much as they reflect energy. And for that, the region has high value of albedo, and it's considered bright area. On the other hand, we have, if we have a material that is, or surface material that is considered dark, it tends to absorb more energy rather than emitting it back to the atmosphere. And for that, it has low value of albedo. So knowing or understanding the both thermophysical properties and to understand how atmospheric properties can influence the derived surface temperatures and thermal inertia, I chose to study two locations that are drastically different. So one is bright region within a Paris region, and it's heavily dominated by dust. As you can see on your left, it's basically a screenshot of the region that I'm interested in, and it was taken by a mock instrument. And here on right, you can see the dust distribution. So any colors from red to green represents the dust distribution across the study region. And the other region that I'm looking into is the Syrtis Major, a dark region that is relatively dust-free. So the reason why I selected these two regions is basically for comparison and contrast purposes. So as I selected the study region, now I'm doing the albedo analysis using data from TESS data tool just to understand my areas a bit more. So in order to understand whether the dust deposition and removal of the dust over a region could induce changes in albedo, so I wanted to look into different years in order to see if albedo could vary on an annual basis. Why annual basis? Because I know in March year 25 there was a global dust storm, so I wanted to look into the region before the storm, during the storm, and after the storm, just to see whether the dust deposition plays a role in varying the albedo. So on your left, you could see the Syrtis Major albedo distribution across this region. And then we have the albedo distribution across Paris, which is the bright region. All in all, it's quite difficult to come up with a result when it comes to whether the values are being changed. So as you can see on your left side, you could see some brightening happening after the global dust storm. In the bright region, on the left side, in the dark region, I could see a few brightenings happening. However, because of lack of data sets and the resolution, I'm not able to conclude anything. And it's the purpose of this analysis was just to understand clearly what is happening. And then moving into temperature analysis using KRC layer and JMARS visualization tool. So basically, JMARS is a visualization tool that allows the end user to look into and visualize different data sets from different planetary missions. KRC is, on the other hand, is basically a numerical thermal model used to determine the surface temperatures. So how do we get that surface temperature? Is basically the user could input certain parameters, such as the user could specify the location of the study region, the dust opacity of the region, thermal inertia, albedo, and then the model will generate surface temperature. So in order to see or in order to produce surface temperatures for my selected regions, I would like to use I use the KRC thermal model in order to study the sensitivity of the observed temperatures and changes of two parameters, which are albedo and dust opacity. In both case scenarios, I'm looking into a bright region and as well as a dark region. And within that regions, I'm focusing on a dusty season, that is LSABS 270, and non-dusty region, which is LSABS 90. And under each case scenario, I'm looking into different points just to get a more context. So in here, I will showcase the work have been done for opacity, for example, purposes. So here, as you can see, the results that I got from the KRC layer from JMARS. So basically, I used the KRC thermal model in JMARS to select a region of interest that I would like to study. So using that layer, I was able to produce the first value, which is the control value. And for that, I specified my LSABS to be 270 because my test scenario here is dusty region, dusty season, as well as dark region. And using that control region or control point, I've been rerun the model twice by changing only the opacity value by incrementing by plus or minus 0.1. And as you can see here, thermal inertia values are same and other values are exactly the same. So, and then what I'm getting is basically the temperature. The temperatures are not exactly the same. Why? The reason for that is basically each test scenario is a different test scenario, atmospheric scenario. So my plan is basically, I wanted to understand how much it takes to change thermal inertia to match the temperature of the control. And for that, what I'm doing is next is changing the thermal inertia in each test scenario and then producing the temperature to match the temperature that are in the control. So in control, as you can see, my temperature is 264. And then I'm changing the thermal inertia, as you can see here, in order to get temperature values that are similar to the control value. And I'm trying to fit the curve to the 2 p.m. Why I'm doing that at 2 p.m. only? It is because the KRC layer basically uses data sets from test data or test instrument, and test instruments measure the surface temperature at 2 p.m. only. However, when we will have our Emirates Mars mission data sets, we will be able to observe these changes over all the day or all the hours. Similarly, I'm doing the same for non-dusty region. In this case, I'm only specifying the LSABS as 90. Why? Because LSABS 90 does not have a dust. And then changing the thermal inertia similarly, and I'm fitting the temperature to the 2 p.m. So that was my presentation for the my project. So as a future work, I need to focus on analyzing further points within selected study regions to have a better context, and then comparing the both results of the two regions, bright and dark, to understand whether how different they are. And the results of this work will be presented at AGU virtual conference this year. Thank you. If you have any questions, I'm happy to answer them.
Thank you very much, Nora. Nora, I'm just going to ask you one or two questions here. What is KRC in GMRs, and can it be accessed by anyone?
Mm-hmm. So KRC is basically a numerical thermal model that allows the end user to input parameters, and based on that parameter, it creates a virtual environment. And through that virtual environment, it extrapolates the temperatures or the surface temperatures of selected area. And yes, it can be accessed by everyone or anyone, and it can be downloaded straight from its website. We could include the link in the chat box. Yeah.
Okay, perfect. And why does this study focus on seasonal changes rather than annual changes?
Mm-hmm. So as I showcased here, so annual changes for thermophysical properties are not profound, and it is therefore I chose to study it on seasonal basis, where the effects or changes are mostly profound.
Yeah. One last question here for you, Nora. What's the reason behind using test data for analysis?
Mm-hmm. As I mentioned in my presentation, KRC layer uses test data sets only, and it is only measured at 2 p.m. And that is the only reason. So we have a limitation when it comes to data, and that's why. But it will be, hopefully the study will be done later on using the EMN's data, inshallah.
Great, thank you very much, Nora. Now we will move on to Khalid's presentation on the EMERS data simulator.
Can everyone see my slides?
Yes, but it's on the presenter view. Yeah.
Okay. So, hello everyone. My presentation is about developing a forward radiative transfer model. So a brief introduction and outline to this presentation is that I'm going to describe how I developed my lower atmospheric radiative transfer model in order to obtain EMERS spectra. So we're going to go into detail for every step that was developed. However, as you can see that there are two arrows indicating that we can do the EMERS spectra. That is because the model turns out to be done without scattering, and then to increase its accuracy and fidelity, we introduce scattering into the model and then develop EMERS spectra as well. So the first phase is research. In research, I started off by reading about the margin atmosphere, especially the lower atmosphere, because that will be my area of expertise when working at MBRC. And I also excelled my knowledge in the instruments I'm working on, which is the Emirates Mars Infrared Spectrometer. Other than that, I started to also enhance my coding skills. So I personally use Fortran. However, many other coding softwares could be used, such as MATLAB and Python, in order to develop the model. And finally, of course, for every data we released, we publish it to the science community, or we present it at conferences such as AGU in order to obtain valuable feedback from the science community. And that feedback helps us enhance our model and introduce new ideas that we have not been thinking about when developing the model. So in terms of model development, I wanted to create a model of the lower atmosphere in order to later on develop EMERS spectra. I started off by just making a very simple model of surface temperature and atmospheric temperatures. And then I slowly enhanced the model by increasing the amount of layers in the atmosphere within the model. The number of layers that have been put into the model depends on how accurate I really want the model to be. And finally, after embedding all of that into one, I could develop the radiances required. So the layers and the surface, we're going to talk into a bit more detail about the characteristics and the constituents that were embedded into each one. So in terms of temperature, in terms of temperature, so the Emirates Mars Infrared Spectrometer, has a heritage instrument, which is called the Thermal Emission Spectrometer TESS, which is developed by ASU. This device also measured the temperature of the margin atmosphere and measured constituents such as dust, water ice, and water vapor, all of which are going to be measured by EMERS. So embedding that mission's data into the model has been really helpful in developing the lower atmosphere. And then, however, TESS did not define the entire margin lower atmosphere as EMERS will in the future. So we also had to integrate that model by introducing the Mars Climate Database, which is developed by LMD. And that gives us a more general type of information about all of the lower atmosphere constituents and temperature and all of that. Making sure that these two can be integrated properly gives me reliability and a nice way to move forward, knowing that all of the data obtained from the GCM and from TESS are reliable and accurate. This is just a plot to show you the amount of missing data that TESS has not measured. And hopefully in the future, EMERS is going to measure the entire margin globe. So after integrating and developing a model from base to 50 kilometers, we then introduced the instruments characteristics into the model. We introduced the noise of the instruments that will help us later define parameters such as uncertainty and scattering. And we also introduced the CONOPS of EMERS, so the observational strategies. We introduced these aspects because at the end of the day, we want to develop a model that is based on EMERS. So the CONOPS helps me to identify the longitude, latitude, the seasonal variations, the time of day, and all of that, all of those aspects that should be measured in the future by EMERS, and we can embed those aspects and parameters into the model in order to develop an EMERS spectrum. So as you can see, as I mentioned earlier, the parameters that were adjusted based on the observations of EMERS and the CONOPS of EMERS, so the concept of operations of the entire spacecraft, are the longitude, latitude, L sub s, local time, Z coordinates, and emission angles. Utilizing these parameters, we develop model outputs. So in terms of output, I choose what outputs are required from the model. And I have chosen these specific outputs: the total water, total ice, total dust, the atmospheric and surface temperatures, and the surface pressures, because they are the key constituents that will be measured by EMIRS in the future. And as you can see, when we measure the radiance, or the radiance obtained from this model can be also converted to brightness temperatures, and spectrums could be produced. So we talked about uncertainty. We introduced the instrument noise, and we vary that with the change in radiance to obtain uncertainty. So in general, uncertainty is how well we can actually obtain results from specific areas. And as you can see, these are two constituents. On the left-hand side, we have the uncertainty of dust at the equatorial region. And on the right-hand side, we have the uncertainty of ice at also the equatorial region. The less the uncertainty, the better it is in developing the retrieval algorithms, and the easier it is to develop algorithms in the future to obtain data on dust or water ice or any other characteristic. And finally, into the model, or should I say the most recent update to the model, is introducing the scattering streams. So I first developed the model in order for it to produce limited amount of data, as you can see here, but then integrated more parameters into the model and obtained the scattering stream for a range of parameters, not just one or two parameters, in order to identify plots like these. These plots show us the number of scattering streams in each region, and this plot shows me the different scattering streams based on latitudes and seasonal variations. And we require scattering streams in order to first identify how much streams are needed for our retrieval algorithms in the future, and to further enhance the spectrum that's going to be generated by the model. So when we integrate everything into the model, taking into consideration scattering streams and the GCM outputs and the uncertainty, we can finally produce brightness temperatures from the radiances obtained from the model. These brightness temperatures help us in identifying objective A, which is to characterize the state of the margin lower atmosphere on global scales and geographic, diurnal, and seasonal variability. And that objective will help us answer the AMM question about the margin lower atmosphere and how it responds globally and seasonally to solar forcing. Thank you.
Thank you very much, Khaled. That was an excellent presentation. I'm going to just ask you a few questions here. Instead of finding out the number of streams in every condition, why don't you just choose a high number of streams that meet all the conditions that you want?
Yes, so we go into work in finding out each constituent and each condition, the number of streams for that condition, because if I just chose a very high number of streams for everything, it will meet the requirements. However, the amount of time that will needed for it to process will be much, much higher than if we know the number of streams is less and choose the lesser number of streams.
Thank you. And I believe you mentioned somewhere that you chose the vertical height of 50 kilometers. Why did you choose that in specific?
Yeah, so the model is generated purely to obtain spectrum of EMIRS. And the EMIRS is going to measure the constituents and the temperatures from the surface to 50 kilometers above surface.
Okay, and can the model be altered or changed to produce more outputs?
So the LND GCM has a lot of other parameters which are included into their model, which can also be embedded into this model. So yes, I can technically choose whatever output I desire. However, I focused on these specific outputs because I'm working on the lower atmosphere and I'm working on the EMIRS Mars Infrared Spectrometer. So those are the outputs and results that EMIRS is going to measure when reaching Mars.
And one final question. You mentioned by the end of your presentation about uncertainty. So if you have a large uncertainty, such as the red regions that were specified in the plot, will we not be able to retrieve data?
We will be able to retrieve data, yes. The only thing is that the retrieval algorithm will be much more complicated, and it will need a lot more processing. However, data can be retrieved even if the uncertainty is high.
Perfect, great. Thank you very much, Khalid, for your time and
Thank you.
presentation. Now we will move forward with Iman Al-Taneji for the EMERS footprint mapping presentation. Yes. Iman, I believe you muted yourself.
Okay. Good afternoon. My name is Iman Al-Taneji. I'm an EMERS instrument science engineer. So as we mentioned last week, EMERS Mars mission has 3 instruments on board. 2 instruments to study lower atmosphere, which are EXI and EMERS, and 1 instrument to study upper atmosphere, which is in use. So EMERS, it stands for EMERS Mars Infrared Spectrometers.
Iman, sorry, your voice is not very clear.
What about now? What about now?
Yeah, much better.
Okay. So EMERS instrument stands for EMERS Mars Infrared Spectrometers, and it's developed by Arizona State University and Mohammed bin Rashid Space Center. The spectral resolution of the instrument is equal 5 centimeters, and the spectral range from 6 to 40 micrometer, while the spatial resolution from 100 to 300 kilometer resolution. So the objective one of an EMERS Mars mission is to characterize the global state of the Mars lower atmosphere and its geographic, season, and daily variability. So EMERS will measure the global distribution of water ice, water vapor, and dust, and surface temperature. And in regards to second objective, EMERS will provide the linkages from the lower to upper atmosphere in conjunction with EMUSE and EXI. EMERS has 2 observations, and these observations are done 20 times per orbit in the nominal science orbit. It means it takes 60 observations per week, and the duration for observation is 20 minutes at periapsis and 8 minutes at apoapsis. So it observes half of Mars with resolution less than 300 kilometers. So what is thermal infrared radiation? This figure shows the electromagnetic radiation spectrum, which are infrared or near infrared and the thermal infrared. So EMERS is in thermal infrared and are found in longer wavelength. The mineral absorbs and reflects thermal IR differently, and each has own spectral signature in this wavelength. So how is thermal infrared is viewed? So to create the full spectrum of infrared light, we use interferometric device. It's like the prism. So if the atmosphere and surface are different temperatures, then we can see the spectral features. So as Khalid mentioned, this figure shows the spectrum of thermal emission spectrum data, and the spectrum of EMERS will be the same. So the atmosphere of Mars is almost transparent at 1300. So the brightness temperature at that wavelength is used to determine the surface temperature, while CO2 is used to determine the atmospheric temperature. The water vapor has narrow absorptions between 200 and 400 centimeter, while the dust has V-shapes and centers about 1075 centimeter, while water ice have ball shapes and absorption centers at about 825 centimeters. So thermal emission spectrometer is on board the Mars Global Surveyor. It's the US mission developed by NASA to study the atmosphere of Mars. And this mission is ended in 2007. So this figure shows that this data from Mars year 24 to 27, and it shows the variability of the physical parameters of thermal emission spectrometers, which are dust, will water ice, will water vapor. So Mars has polar ice caps made of CO2 and H2O as shown, and this ice supplemented during the spring and summer. So to study the polar gaps, we need to remove the ringing from the data, convert the radiance to brightness temperature, and last step is binning the data. So I will talk about each step in details. So the ringing correction technique is used to smooth and remove noise from data. In this figure, so the red spectrum is the original spectrum, while with the ringing, and the black spectrum is the result after using the correction. And the second step is to convert the radiance to temperature. So to obtain a surface temperature of Mars, first the obtained radiance from an instrument should be converted from radiance to brightness, each at its specific wavelength. So the following equation we use to convert the radiance to brightness temperature. And the third step is binning technique, and it used to make literates easier by calculating the average or the median of the data. So there is much difference between there's no difference between the mean and the median as shown in the figure, but it's still better to use the median to reduce the effect of outliers. So a series of polar gaps plots are made to see how the south polar gaps change with the season. Same previous steps are applied to find the surface temperature and approve if the poles is covered by ice or not by looking to the surface temperature. So in this example, I only look at the south polar gaps because we have many observations over the south poles, and this data have never been used before. So this is the nighttime observation, and the second one for daytime observation. And this is another example for global mapping using same data, thermal emission spectrometer data, to study the surface temperature for different instrument observation from 160 to 270 Kelvin. Yeah, thank you.
Thank you very much, Iman. I'm just going to go ahead and ask you a few questions. What's the heritage of EMERS and how is it different?
Yeah, EMERS builds on long heritage, including thermal emission spectrometers, Minitis and Otis. And if we compare EMERS to heritage line, it has the smallest field of view. It's equal 6 milliradian. So it's enabling small footprint from large distance. It has the higher spectral resolution. It's equal to 5 centimeter. And the wide spectral range from 6 to 40 micrometers.
Okay, and from the plots, how do you know if the polar cap is covered by ice or not? By looking at which physical parameter, basically?
Yeah, we can't tell if the area is covered by ice or not by looking to surface temperature. So if the surface temperature is 150 or less, it means this area is covered by ice. While it's bare ground if the surface temperature warmer than 150 Kelvin.
Okay, and why are you using the binning technique and how does it work?
I used this technique. It's an example of binning algorithms, and it works by calculating the average or mean for example, for test data to make the trends easier and to study and analyze these data to make it easier.
Okay, perfect. Thank you very much, Iman.
Thank you.
Now we'll move to the next presentation, which is the dust storm effects on water vapor and hydrogen in the Martian atmosphere by Hour Al-Mazmi.
Thank you, Mosa. Let me share.
Iman, if you could close sharing your screen.
Can you guys see my screen?
Yes.
Okay. Great. So my name is Hour Al-Mazmi. I'm an EMM science data analyst, and I'll be talking about dust storms on Mars and how they affect water vapor and hydrogen. So you've probably seen this picture before, and my colleagues have spoken about the other instruments as well, or all 3 instruments. But the HOPE probe is currently carrying 3 instruments on its way to Mars, and each instrument is going to be looking at different constituents at different parts of the atmosphere. But today I'll be talking more specifically about dust storms and how they affect hydrogen, which are both things that are going to be seen by the Emirates Mars mission, the HOPE probe, using the science instruments on board. So you might be wondering why we care so much about dust storms, since we have dust storms here, specifically in the UAE, and what's so special about them. You can see, like on the left, dust storm developing from the Mars Curiosity rover. So dust storms tend to get more intense on Mars, but I'll be talking to you about their effects on the atmosphere specifically. And so far, from what we've seen since we've started looking at Mars, we've noticed, so on the right plot, on the right side of my plots, you can see the dust over an entire year. So the y-axis is a time measurement called solar longitude, and you can see the entire Martian year, and each row is a different year. And you can see the dust patterns over latitude. So the top part of each plot is the North Pole, and the lower part is the South Pole, and in the middle is the equator. And you can see sort of a general pattern of the dust storms starting on later on these in the second half of the year. So that's usually called the dust season, and they've been defined when they're regional and when they're contained to a specific altitude by CAS in 2016 to be A storms if they start at the beginning of the dust season, and then later on you have lower southern pole dust storms that are defined as B storms, and then later on you'd have C storms. So you can sort of see that in these different Martian years, where you can see the A storms and the C storms and the B storms. But sometimes you do get some random dust activity. And that's something that's called a global dust storm. And global dust storms are defined as dust storms that cover the entire planet. So you can see that here in this Mars Global Surveyor image, where the planet starts off where you can see its features, and then as the dust storm covers the entire planet, you start seeing less of the surface features of the planet. And you can also get more smaller localized storms like the ones seen here from Mars Express. And this one later on develops to become a global dust storm, similar to what we saw before. So why do we care about dust storms? Dust storms can affect the thermal state of the Martian atmosphere. So you can see that in these plots again on the x-axis, it's a unit of time, the solar longitude, and each line represents the beginning of a new year. So the top plots show you the dust events or the dust wavelength, basically the opacity, and the bottom plots show you the temperature. Now, during the same time as the dust storm season, we're also in the southern summer period, and the planet gets closer to the sun, so temperatures tend to be higher. So you may think that maybe this temperature increase is because of the seasonal effect and not because of dust. But we also see a corresponding temperature increase compared to other years where there's less dust. We see an increase of temperature as a result of increased dust. And then dust storms can also affect the circulation of the planet and the atmospheric composition. So you might have seen something about cloud seeding in the UAE in the news recently or in the summer. So a similar process occurs in the Martian atmosphere, where if there's dust in the atmosphere, the dust particles act as seeds for carbon dioxide in the atmosphere and water vapor in the atmosphere, where these constituents condense onto the dust particles, and then they become ice clouds, or that can later fall back down to the surface. And this is a very similar process to that seen in cloud seeding, where salt particles are thrown into the air through jets, and they cause clouds to form and result in more rainfall. So as I mentioned before, dust storms also improve the circulation of the planet, so they make it more intense. So the planet naturally has a circulation that occurs, that changes with the season. So as the planet gets, the planetary tilt, if it's aimed towards the sun and the southern hemisphere, for example, as seen in this picture, has the southern pole exposed to the sun rays or the solar rays, the southern hemisphere is going to be hotter. So warm air will rise and will continue to rise until it gets to the colder hemisphere. And then and it will become cold, so the air will descend. And because of the increase in temperature that occurs because of dust storms, that circulation is intensified as well. So you would get water vapor getting to higher altitudes, or water vapor moving to the more rapidly because of the intensified circulation of the atmosphere. So as a result of the intensified circulation, and as a result of the higher temperatures that are seen during dust storms, water vapor tends to get to higher altitudes. And the hygropause, which is the highest point where water vapor gets in the margin, in the atmosphere in general, becomes higher. So with water vapor higher in the atmosphere, photolysis, which is the reaction of light rays with water, results in hydrogen, and hydrogen is higher in the altitude, which allows it to rise higher in the altitude, and it escapes the atmosphere. So that all of these things begin with a dust storm at the surface and result in atmospheric escape of such an important constituent, which is the hydrogen in the upper atmosphere. So my project, or my research, is mostly concerned with what I just explained, but I'm doing it currently more through a computer simulation, or a simulated margin atmosphere through the LMD-GCM, which is the General Circulation Module, which is very similar to what is used to predict weather for Earth models, but this is being done for Mars. And this model uses reconstructed dust storms that are made based on observations of the dust storms that develop on Mars for each year. So as I mentioned before, margin dust storms do have a pattern, but they're also very random. So it's important to use observations to put into the models to see how it affects the rest of the atmosphere. And this is an example of my research and what I do. So I basically look at how in this plot, for example, I compare a low dust scenario with the latest Mars year dust event, and see how it affects water vapor in the middle atmosphere, and then as a result affects hydrogen in the upper atmosphere, to see the quantities of hydrogen escape as a result of different quantities of dust and how intense dust storms are. So EMM will hopefully tell us a lot more about how what the relationship between dust storms in the lower atmosphere is with the hydrogen escape in the upper atmosphere by looking simultaneously at the lower atmosphere and the upper atmosphere, and studying the effects of dust storms, and studying dust storms by having diurnal coverage of the planet through the instruments on board. That's it.
Thank you very much, Hur. I have like two questions coming your way. Why are dust storms on Mars so significant compared to the ones on Earth? Yeah.
So because dust storms, because Mars is a much smaller planet and it's much drier compared to Earth and has a much thinner atmosphere, things that the radiative effects of dust on Mars is much more significant compared to on Earth because we have a much more complex atmosphere. So these effects tend to propagate and result in something as significant as atmospheric escape.
Thank you. And why is it important to understand the rate of hydrogen escape from the atmosphere of Mars?
Observations have shown patterns of flowing water on the surface of Mars. And since hydrogen is such an important constituent or such an important part of water, looking at hydrogen escape will help us understand how Mars lost its water that used to cover the surface of Mars and its atmospheric escape better.
Great, thank you very much, Hur. Now we'll move forward to Fatma Luta's presentation on the forward modeling of oxygen in the Martian atmosphere.
Can everyone see my presentation?
Yes.
And is my voice okay? Can you hear me?
Yes, loud and clear.
Okay, great. So hi, everyone. Thank you for joining us today. Today, I'm going to talk about the forward model I built to predict how oxygen looks like in the Martian thermosphere. I am Fatma Luta, and I'm instrument science engineer working on the Emirates Mars mission. So I just want to go over first the development methodology we used for the forward model that I'm going to present today. Each researcher or each scientist has their own preferred development methodology, but I think it's going to be beneficial to go over this to see the approach that I decided to take with my mentors. So first off, this is, I guess, a must for every model is to define your science objective of the model and what do you want this model to produce. You have to do lots of literature review of the thing or the constituents that you would like to study and understand more in the Martian thermosphere or atmosphere. In our case, we started first by designing a simple toy model as a beginning of this project. And I'll go through all of this in details in my next slides, but this is just going over everything in the beginning. Later on, after getting some results from our toy model, we were confident to design the entire radiative transfer model. We then go to try to verify the results that we're getting from the radiative transfer model. Finally, we work on optimizing how can we better make these results accurate, what can we add to the model. So the project I'm going to showcase today is aligned with the Emirates Mars mission's science objectives and investigations. We did present this breakdown in one of our past sessions, but this is the science questions and objectives and investigations and how they're related to the instruments that we have. Specifically for the presentation I have today, the work that I work on feeds into the investigation of understanding the distribution of key neutral species in the thermosphere. The Emirates Mars mission's EMUS is going to detect two oxygen bands, oxygen 135.6 nanometer and 130.4 nanometer, but today I'll be talking about the modeling for 135.6. So here we go to the first step of the development of this model, which is defining what was the objective of this model, what did we want it to fulfill. Currently, the model is completed and is verified, but we are using it constantly for different science analysis and to run different scenarios. So the main objective for this was to try to predict how UV emissions in the thermosphere of Mars are going to look like if the instrument EMUSE captures these images. And it was very important that this model can support science closure tasks and so on after we do receive data from EMUSE. Going into literature review, just giving some information about the band here. You can see that I bordered it here, oxygen 135.6. What do we know about oxygen? It's an optically thin emission. The major source of this emission is electron impact on the atomic oxygen of that band. It is quite dominant in the homopause of the Martian atmosphere, which is around 130 kilometer. The homopause is like a transition point where the constituents below it were very well mixed, and then above that region, the species begin to separate according to their unique masses and different scale heights, whether it's through atomic or molecular diffusion. So here, when we started getting our hands dirty and starting to create this model, we decided first off to start designing a simple toy model. So what do we mean when we say toy model? So basically, it's a hypothetical model where we have to add minimum amount of parameters to generate results. So it's definitely not the best interpretation of oxygen, but it's just the beginning step. It follows a lot of assumptions about the atmosphere's behavior. So why did we decide to take this step? First off, it was a very good training to start in radiative transfer modeling, getting used to the programming language, introduction to the concepts of modeling. It was a very good start to understand how oxygen might behave based on values that we got from literature. And it was a great baseline to start before building a radiative transfer model. So what did our simple toy model have? And how did we approach this? First off, we assigned a simple scenario from literature. So instead of going through so many seasons, so many different solar minimums, maximums, and moderates, we decided just to choose one scenario. And the scenario we chose was at 130 km homopause, season 97, LS 97, minimum, solar minimum, and it was at nadir viewing. We had our assumptions done. We were assuming that oxygen is optically thin. We assumed an isothermal and hydrostatic atmosphere. We chose input parameters. We chose volume emission rate calculation by Chapman profile concept. And we used, so basically we took a hypothetical peak from literature. In this case, it was around 10. And then we used calculation from Chapman profile. So very simple assumptions of the atmosphere to be able to generate some results. We used simulated geometry of Mars provided by the EMUSE team we have. So this was simulated geometry of what we expect the EMUSE instrument to provide. So we tried to incorporate some physics of the atmosphere and used column emission rate calculations through Chapman profile theory as well. And then we evaluated the results. So we did our troubleshooting, our debugging, and then we went ahead and we were changing the contribution of atomic oxygen and CO2 on the band itself, and we had to conduct some sensitivity analysis. So this is just an example of what was produced from the toy model. As you can see here I was playing with the percentages of how much I was expecting oxygen and CO2 to contribute to the band. And obviously, the more we expected atomic oxygen to contribute, the brighter the image that we received. And this was just a sensitivity analysis. In our radiative transfer model, this is automatically calculated for us, so we don't have to play around with percentages. The physics that we coded already bring it out for us. So, like I said, we used around 10 from Fox and Delgarno's paper in 1979 as a peak. And again, to add, when we do a radiative transfer model, we calculate the peak automatically rather than just inserting some literature point that we have received. So designing radiative transfer forward model. So after we were quite confident and happy with the toy model as an introduction, we decided to move and build our design radiative transfer forward model, which has taken a lot from the toy model, but was much more complex and advanced. So this is just an example of the kind of scenario we can choose. However, we can choose different scenarios as well, which make this model unique. So for example, this was assigned as at oxygen at homopause, which is 130 kilometers, LS270, but this model can run different LSs, and I will show later on some results from different kind of LSs. And the solar moderate is a good scenario to test out. But the good thing about the radiative transfer model is we were also able to run solar maximums and solar minimums. So it has that kind of extra options from the toy models. So we have the same assumptions as before, but we're also assuming that Ergo is at the altitude of the homopause, and we're also assuming as the isothermal atmosphere. So for input parameters here we got an entire densities and an entire database, a data set from the Mars Global Ionosphere Thermosphere model to calculate volume emission rates. So instead of the toy model of just inserting a volume emission rate peak, we were able to calculate, build a model that calculates volume emission rates for us. And we also used the geometry of Mars provided by the EMUS team. So when you're working with a big data set, you have to do a lot of filtrations. In our case, since we sampled at the homopause, so we filtered out the data and made sure that the data was sampled at 130 kilometers. We filtered out anything that was above solar zenith angle and emission angle 80. These are the lunar longitudes and latitude points that we looked at. And then we had to bin the data with respect to the above, these pointers that we have. So adding the physics part to the model, column emission rate calculations, we used plane parallel approximation for the solar zenith angle dependence. We added something that we didn't have before in the toy model, which is to be able to calculate everything. We needed electron impact on oxygen cross sections and stimulation frequencies. We also did normalization Mars to sun distance normalization through all our inputs to make sure that everything was consistent. Again, we evaluate our outputs, troubleshooting and debugging, which is part of anything that does with coding. We changed the scenario and conducted different sensitivity analysis to see what kind of results that we produced. So basically the radiative transfer model and the results I'm going to show now is we have to put the atmosphere physics, we used density of oxygen and density of CO2, solar zenith angles and emission angles from the geometry files that we received from our team to be able to get the brightness of oxygen in the Mars atmosphere, specifically in the thermosphere with different viewings. So I just want to showcase some things that we got from the model. So this is at LS270 and it's already corrected with the Mars sun's distance. So here we actually can run two different geometries. We run a full Mars EMUS geometry. So this is images of oxygen 1356 sampled at 130 kilometers, different solar cycles, and what we imagine to get the image from EMUS. And we have below here a comparison is when I run different geometries similar to the MAVEN mission, NASA's MAVEN mission, and how different the viewing looks like. So other products that I was able to produce from the model is the distribution of oxygen on longitudes and latitudes. Rather than just a 121 by 121 pixel image, I am able also to produce it on longitudes and latitudes. And here I have it produced at 3 different seasons, LS0, LS270, and LS90. And this is great for us to compare what we expect from brightnesses to change, understand what could be the factors that make brightness more bright in a specific season and so on. So this takes more analysis to understanding why are we seeing what we're seeing. And I just wanted to showcase some of the products that we can get from the 4WIND model and how it can be benefited from. So verification of the radiative transfer model, how can we verify that this model is working? In the end, we created this model. So the approach that we took was comparing the results from the radiative transfer model with a simple hydrostatic model based on plane parallel approximation. We are checking out, does everything come in line, and do they follow the same patterns? Another thing that we did was run another data set from a different set. So different data from MGIRM. So what we used earlier was data from MGIRM, which is an online database, but you can also run different data on the radiative transfer model, and it also helps us to verify if the model is working as such, because even if we change the data, it's supposed to work well. So it's a kind of approach we take. And then we conduct sensitivity analysis to verify, okay, is the model working? How accurate is it, and is it not? So plane parallel approximation, brightness is supposed to be A, which is brightness at nadir point, times cosine solar zenith angle, and then cosine emission angle, and fitted on a specific point, specific value. So based on our research, we have, that's just a long explanation, but let's just say that we have set the value for cosine solar zenith angle to be 0.5332 for atomic oxygen. So we expect that this equation shows us the behavior on oxygen based on plane parallel approximation. So in the graph, you can see cosine solar zenith angle at 0.5332 and how it changes with solar zenith angle. And we see that the output from the model follows very similarly what we expect from the plane parallel approximation. Now, of course, there is some differentiation here in the end, but this usually is expected at high emission angles. And again, our radiative transfer model has much more parameters than the plane parallel approximation, but at least we can tell that it is quite following the same approach. So this is the same plots that I just showed, but one thing differently we did was we, instead of running oxygen from MGIRM, we used different test profiles that were produced actually by my mentor, and we ran them as well. And we saw that the brightness produced also followed kind of the same pattern. But here I have 3 plots because here we were playing around with eddy diffusion scenarios, different Ks, and that also shows that, again, when we go back and we look at the databases, every database is sampled at a different eddy diffusion. So this is another thing to look at for. So there's always a lot of parameters to put in mind when you are trying to verify your model and when you're trying to compare results using different data. Optimization of the radiative transfer model. What else we can add to make this model more accurate? One of the things that we were looking at was to add the CO2 absorption effect on the atmosphere of oxygen 1356. These are some plots that we created when we added the CO2 absorption and how it affected both CO2 contribution and oxygen contribution to the band as well as the total band. So it was also interesting to see, and that's another factor that we can add to make our model more accurate. So as a whole, these are the steps we took to produce our model, and these are some of the products that we are able to receive from the model. That's about it, and thank you.
Thank you very much, Fatma. I wanted to ask you, what programming language did you use to build this model?
So first off, when I started this project, I actually started using Python coding language. And then afterwards, I moved to IDL. And actually, the reasoning for that was A lot of the inputs that I put into my radiative transfer model, such as the stimulation frequencies, the geometry, were produced by some scientists in our team, and they were in IDL format. So it was more convenient to have my radiative transfer model in that language to be able to easily read all these kind of inputs. So my model is developed using IDL.
Okay, great. And can this forward model be applied to other constituents in the atmosphere?
Yes, so actually I used the same, I will call not the exact same model, but the foundation of this model, I used it also to run argon densities as well as carbon monoxide for PG bands. So as a foundation, I was able to reuse this for other constituents, but again, every constituents, their physics are different and their impacts are different. So for carbon monoxide, there's different impacts on carbon monoxide, not just electron impact. So you usually have to add and make some changes, but it's always helpful that this is a baseline now for other constituents that I've been using.
Great. And what are the challenges that you faced while building this model?
So you face a lot of challenges. It's a learning curve. So in the beginning, it is quite challenging when you're learning a new language, as I didn't know how to use IDL before. But you do, I think one of the challenges is when you're trying to recreate something and you're just stuck and you just need time to overcome it. One thing that I faced a lot, and when you're using very big data sets, sometimes you will get results that don't make sense. So it's very, very important to make sure that you filter and reduce your data in the most efficient way possible to make sure that your results are accurate.
Perfect. Thank you very much, Fatima, for your presentation. Now we'll move to Hassa Al-Matroushi, where she will be presenting about oxygen in response to solar activities.
Thank you, Moza. Fatima, can you stop sharing? All right. So this is Hassa Al-Matroushi, EMM Science Deputy Project Manager, and I'm here to present to you my research project concerning oxygen in response to solar activities. All right, so let's start with background information about oxygen. So if you see the graph that I have up there, so this is the density profiles when it comes for oxygen and CO2. As you can see in here, below 200 kilometers, CO2 dominates the neutral species in the atmosphere. But as we go above it, especially like up to the lower exosphere level, then oxygen is the dominant one. And above 200 kilometers, we have atmospheric escape happening. So oxygen does escape the Martian atmosphere of Mars. So that makes it a very interesting constituent to be studied, especially at this kind of level in the thermosphere of Mars. If we want to study the oxygen, we can do that using several emission lines. One of them is the oxygen 135.6 nanometer emission. The reason why I've chose this emission to study and not the other ones is for several reasons. One, oxygen 135.6 nanometer emission is optically thin compared to the oxygen 130.5, which is optically thick. This kind of oxygen is excited mainly by electron impact on oxygen and CO2. And if you take the intensity of it, then it's very much proportional to the oxygen abundance. So the densities can be derived very easily using this kind of emission. And that's why I'm using it in this kind of research. One of the recent missions that have observed the oxygen in the Martian atmosphere, specifically in the thermosphere, is MAVEN. And here you can see a disk image that was taken from MAVEN. This is the disk image of Mars using the oxygen 135.6. And this is the current data that I'm using right now for my studies on the oxygen in the Martian atmosphere. Here, this is a diagram just to explain the parameters
that can impact the detection or the observation of oxygen. So here we have the spacecraft. Let's say this is the Hope probe, and we're observing and looking into Mars by the instruments that we have. So there are a lot of parameters, geographical parameters that we need to take into consideration. For example, where are we observing the oxygen in terms of longitude, latitude, in terms of altitude as well. And there are other things which are more concerned about the observation, like the emission angle. Basically, this is the angle between the spacecraft and the zenith. And then we have the solar zenith angle, which is basically the angle between the sun and the zenith. So that has an impact on the value of the oxygen that we observe. And then we have the Mars-Sun distance. So as the probe is orbiting Mars, the distance between Mars and Sun changes, so that can impact the oxygen brightness as we get closer and further away from the Sun. And we have as well the solar activity. So basically the Sun has its own activities that can impact the oxygen in the Martian atmosphere, so that we can see the brightness varying accordingly. In here, I'm highlighting 3 parameters: the emission angle, solar zenith angle, and Mars-Sun's distance, because these are the 3 parameters that I've started using when I tried to model the oxygen in the Martian atmosphere. And unlike Fatma's presentation is more of a forward radiative transfer, more of theoretical approach. In my approach, I've been using IVS data from MAVEN mission. So it's more of an empirical approach, like looking at the data, trying to see what kind of information it gives us in response, and then doing the model accordingly. So here I would present the results from the empirical model that I have for oxygen 135.6. First of all, this is a graph, an image that shows the brightnesses. So these colors are the brightness. We have in the x-axis is the emission angle. We have on the y-axis the solar zenith angle. So basically, as the emission angle increases, then we notice that the oxygen brightness increases as well. But as we go vertically, as the solar zenith angle increases, we notice that the oxygen brightness decreases. So there is an inversely proportional correlation in between. So we took the data, and this data was taken from consecutive orbits, 16 consecutive orbits. So we can average any longitudinal effects when it comes in the data. And it took these 3 parameters into consideration. So the Mars-Sun distance was normalized when it comes to the data. We took the data and then produced the model according to this data, and this is what I got. So I did this approach for 2 different models. So we have 2 different equations in place, empirical model 1 and then empirical model 2. You can notice that both of them yielded to a similar result, which was good, which means like they are mimicking the data that we have from IUVS in a very good manner. So one way to check how well the model is working with the disk data is just to subtract them both together. And this is what we get. So this is the model subtracting the data from it. And whenever you have white dots, so this is basically they're matching perfectly. And then whenever you have positive values, you will see them in red, and then the negative differences, they would be in blue. So in all, if we look at the error values, like they range between positive and negative 30 Rayleighs, which is not that big, which means like this is a good matching in between them. And you can see like that the greatest values occur at higher emission angles. So that's something to take into consideration as well. So when this effort was developed, we could notice that the brightness vary with the observation geometry as expected. This is what we wanted to model because we know that the oxygen behaves differently depending on these parameters. But we've noticed that there is evidence for time variability. So there are some dependencies when it comes to local time or maybe latitude, and even the seasons and the solar activities and so on. So that's why we went into the next step, which is trying to investigate how the solar activity impacts the oxygen brightness. So we can take that and incorporate it in our model. So when we look at the solar activity, like this is a graph that can shows the solar cycle. And the solar cycle, it can be represented by the sunspot numbers that we have. So the one in purple right here, this is the predicted solar cycle 25. This is where we're currently at as we are getting data in here. And the data that we will get from the HOPE probe will be overlapping with this part of the solar cycle. So it would be in a minimum solar cycle compared to the minimal to moderate compared to the ones are here. So we're not in extreme cases when it comes to the solar activity. And that was a good thing because the data that I have from IUVS MAVEN mission are in between here. So we can use the data that we get from MAVEN and the solar activity information that we have and try to do the model in order to anticipate what MU's instrument on board of the HOPE probe would be able to see during the time when the HOPE probe would return the data from the science phase. Okay, so what kind of data did I use in my research? Two different data sets. One is for the oxygen brightness. So the oxygen brightness, as I mentioned, I use IVS, Apoapsis far ultraviolet data from the MAVEN mission. And for the solar activity quantification, I use EUVM level 3 daily data. This is from the MAVEN mission as well. And supplementary to this information, I had the CO2 ionization spectral cross-section. So I've done data treatment for each set of data. Starting with the oxygen, I had to do several things. One, I had to consolidate orbits by date. So like I was looking into consolidating a lot of orbits and representing them only by days, so we can have like less data points to correlate with the solar activities. And then I had to correct the brightnesses by the other parameters, because when we want to study the brightness versus the solar activity, we need to make everything else in terms of observation parameters constant. So one of the things that we did is correcting the brightness by the cosine of emission angle based on the model results that we had. The other parameters, we did filter them. So basically we constrained the sampling of them. We chose a defined latitude and defined local time sampling and a defined solar zenith angle. So we try to make every range consistent. So when we do the correlation, we can have a meaningful result as a result of that. And then after taking all that into consideration, we will compare it to the solar activity. But for the solar activity data, so the EUVM level 3 daily data, we took it and then we did an EUV flex units conversion, and then we calculated the ionization frequency. And the ionization frequency will be the representations of the solar activity. So as it goes high, then that means the solar activity is higher. So both data then were correlated. I calculated the correlation, the covariance, and even tried to do a linear fit in between them to understand how they behave together. Before I show the results, I want to talk a little bit more about the data sets that I'm showing in this presentation. So I do have 3 data sets. I fixed the season. So this is what you see right now. I tried to pick data sets from different years in the MAVEN mission, but with similar seasons. So we can try to fix that to do our study. So they are all around 107 in between. We have a different range because we have around 25 days cycle for data set number 1 and 2. And then for the third one, I have a lower data set available for that. And then other things that I took into consideration while choosing the dates and the sample data that I have is the orbit availability. So that was one of the struggles I have in conducting this project, because I didn't have a lot of orbits available. And if I don't have them all available within a day, that means I cannot trust the daily representations that I got. Because in the MAVEN mission, like I need 5 to 6 orbits to represent 1 full day. And if I have only 1 day available, so this is not a representation of a full day in there. So there would be some biases in the data. So that's something that I have to take into consideration when picking the dates. So on average, like I made sure that I have at least more than 80% of the orbits available within the data range that I picked. Other things that I took into consideration is the zonally average, location sampling, just to make to be aware of them while doing the analysis. So to know where the data are sampled in these different years. So the results for that is as follows. So here we have a graph with a lot of data points. First, let's start with the x-axis. We do have the ionization frequency, which, as I mentioned, is the representation in this research for the solar activity. And then we have the brightness for the oxygen in the y-axis. And then we have data points in terms of clusters. So this cluster representing the 2016 data, this one is the 2018 data, and this one is the 2019. Each data point, each circle represents a day. And we have two different colors in here. We have color yellow, which means that these days I don't have the full 5 orbits available, which means that I need to be somewhat wary and concerned about them because they might not be 100% representative. And the black ones are the days that I have the full data sets present in my hand. So those are more, we are more confident about them. One thing I would like to turn your attention to is the correlation, the one that I highlighted in here. So one thing I've noticed that in the 2016 data, we have these data capture at a higher solar activity, and the correlation is higher in comparison to the 2018 and 2018 data, where we had correlation in here 0.3 and almost none when it comes to the 2019 data. As you can see, like there is no fitting that can be done there, as if there is no dependence in the solar activity in this case. This was done in local time sampling of 1 hour in a specific region, but I wanted to see if I change the local time sampling from 1 hour to 3 hours. That's why having more data points to take into correlation, whether that will change the correlation. And this is what I got. So the correlation values in comparison to the one that I showed just now had a greater values. So here we have 0.75 in comparison to 0.564 before. Here we have 0.46 and this one 0.44, which is almost was none, and now we have it as a stronger value. So that shows us that the more data points we have, like the more correlation between the solar activity and the brightness can be visible in the data. But we have to be concerned when we take like a wider range, whether we are whether we would see other parameters correlation with the brightness occur in this sense or not. So more data, the stronger correlation we found. As I mentioned, the analysis that I've done using IUVS data had a lot of challenges, and this is where I had the spots. So one of the things that I faced when we have the 2016, 18, and 19 data is the integration time. This is something that is not consistent between the 3 data sets. Integration time is the time that the instrument takes to collect photons of light for the oxygen. And the more time we have, the more signal to noise ratio we do have. That means we can trust the data that is returned from the instrument even more. So in the 2016 data, the one that has stronger correlation, we had an integration time which is higher than the ones that we have in different years. So this is in the 2018 data. We have like around 3.8 compared to 14, which is much, much lower than the one we have in here. And then in the 2019, we have it even much lower. Like it can go up to 0.9 as well. So that's something that I'm currently studying, like whether how this integration time will impact the correlation and whether it would give us more confidence into taking the data as is, or should we do some resolving in terms of the correlation that we have to take that into consideration. Okay, so one thing we always fall back into that these analyses are done to familiarize ourselves with how the oxygen is behaving in the Martian atmosphere, specifically in the thermosphere layer. And this would help us understand more the Emirates Mars mission. So the Emirates Mars mission has 3 scientific objectives. One of them depending on the lower atmosphere. The second is about correlating the lower atmosphere with the upper atmosphere. And the third one is about characterizing the exosphere itself. And to achieve these objectives, the whole probe will have 3 instruments. One of those instruments is called EMUS, Emirates Mars Ultraviolet Spectrometer. And this instrument would be studying the upper atmosphere of Mars. So the thermosphere layer that I've been studying so far, in addition to the exosphere layer. And EMUS will give us information about the oxygen 135.6. But one good thing about EMM, and this is how unique it is compared to the other missions and data sets that we already have, EMM will give us information on a good coverage in a daily, timely format, global coverage as well, and in terms of seasons. So the challenges that I've been facing into finding orbit availability, finding consistency, and then limiting the local time, we wouldn't run into when we have the Emirates Mars mission data, because it overcomes all these kind of challenges. So this is where we're looking forward for the data to enhance our understanding that was limited by the current data sets that we already have currently from the spacecrafts orbiting Mars. So in conclusion, based on the comparison that we've noticed between the solar activity and the brightness, we can say that at lower solar activities, we have lower correlation, which gives us some information that maybe the brightness of the oxygen is not dominated by the dynamics in the upper atmosphere. Sorry, it's dominated by the dynamics of the upper atmosphere and not by the solar activity. So it has a minimal effect. However, when the solar activity is higher, it dominates the influence on the brightness, which this was noticed even when studying a dusty season, which was very interesting to see the consistency in between different seasons as well. As I mentioned, this analysis was constrained by the data availability, so it limits our understanding when it comes to the processes that are happening in the Martian atmosphere. And this, inshallah, would be overcome by the EMUS instrument that was designed to overcome this kind of shortcoming from other instruments. This is the end of my presentation. I welcome any kind of questions you have when it comes to this kind of study or else. Thank you.
Thank you very much, Hassa. I have a few questions for you. One basically highlighting the data that is used. Why did you choose to use IUVS data from MAVEN?
That's a good question, Moza. So we have a lot of data sets that are similar to the EMUS instrument, but since we're part of the science team of Emirates Mars mission, our ultimate objective is to gain understanding about the Martian atmosphere and how it will be captured by our instrumentations. And IUVS on board of MAVEN is one of the recent instrumentations that are observing the oxygen in the Martian thermosphere. And the data products it has, it would be very similar to the EMUS instrument. So it's a good proxy to it.
Thank you. And how does this study help us understand EMM science?
It will help us understand the EMUS instrument data products better, because as the EMUS instrument, when it will start the science phase, give us information about the oxygen in the upper atmosphere, we'd be able to understand the changes in the brightness that we get. So we'd be able to reason why we have higher brightnesses in specific times compared to others, because we understand the dependency it has within the observation parameters.
Great. And one final question. Have you studied the correlation of the oxygen and solar activity in different seasons?
Yes, I did. So the graphs that I've showed just now is focused on a season between Alsabas 100 and 110, and I wanted to make them consistency for comparison. But I've done a study on Alsabas 270, which is the dust storm season, and I have in plan even to do another study on Alsabas 0 and Alsabas 90. So I can have a more understanding on how this correlation changes when the seasons change as well.
Great. Thank you very much, Hassa. Now we'll move on to the final presentation by Noura Saeed on water on Mars.
Hello. Hi, everyone. I will be presenting today on water on Mars. So can the panelists hear me all right?
Yes.
Okay, perfect. All right, so this is going to take it back to the bigger picture and a little bit of the basics at the beginning, but bear with me. It will be part of the story of the research that I'm doing, studying water on Mars and how it has changed over time and what it's going through right now. So starting with the basics, Mars is a dry, dusty, volcanic planet with a thin atmosphere. And we know a lot of things about it already when it comes to the geology of the surface and the composition of the atmosphere. So for example, the atmosphere is really thin compared to that of Earth. It is around 6 millibars, whereas Earth, if you're standing on the surface, you would experience 1 bar of pressure. So that's 1,000 times less on Mars. And when it comes to water, there's only 0.03% water in the Martian atmosphere, and it is purely in gas form. It is not in liquid form. And it is very dry in the amount of water that it holds, in that it only has 200 to 500, around 200 to 500 times less water than Earth has. And most of that is stored as ice in the polar caps or as gas in the atmosphere and locked up in the interior subsurface of that planet. So these are the 3 main reservoirs that I just mentioned, and a lot of trying to understand the water cycle is trying to understand how these 3 reservoirs interact on the short timescale, and also how these 3 reservoirs evolve on the long timescales. And here you're seeing just a picture of the polar caps on the left, where from season to season, the water migrates from the north to the South Pole, and it's deposited when it's a winter season in the north, and then sublimated directly from solid to gas in the spring, and so on and so forth. And then in the subsurface, so even at lower latitudes on Mars, you do see buried ice in the topography and below the layer of dust. And this is an image of one of those exposed slabs where you can see ice under the surface. And it's unknown how much ice is stored under the surface because we can only see glimpses of it. And then the last reservoir is the atmosphere. And this is the smallest of all these reservoirs, but it's a very important one because it allows for the water to move around between the 2 different reservoirs and to migrate seasonally and also on longer timescales. And there's a lot of evidence that there was actually liquid water flowing on the surface. It didn't always look as dry, and it didn't always exist as only as gas and solid. So the evidence comes in a multitude of different places. You can find evidence in meteorites. So this NWA 7034 meteorite that was from Mars and landed on Earth. You can analyze its composition and see that there was much more water in the past than there is today because this meteorite came from a much older time on Mars. And then you can also look at the geology on Mars itself. There's a lot of deposited minerals, such as those little so-called Martian blueberries that were deposited at the bottom of an ancient dried up lake that can only form in the presence of water. And then you have geological features such as the one on the right, where there are valleys, rivers, and other canyons sculpted by the flowing of liquid water on the surface. And we know that it's liquid water and not liquid anything else because of the sediments that are deposited at the bottom being formed in the presence of water. And the last one, which is going to be relevant to my research topic a few slides down, is there are isotopic measurements in the atmosphere. And isotopes are just the study of different chemicals and their sister constituents and seeing how they evolve over time. And that tells us a lot about how the atmosphere has evolved and its water content as well. So one of those markers is the D/H ratio, which is the deuterium to hydrogen ratio, deuterium being an isotope of hydrogen. Essentially, it just tracks how much water is moving around and being removed from the Martian system. And you can see a significant increase of the D/H ratio over time on the billion-year time scale. So you can use that as well to learn more about what happened with the water. And all of these are pointing towards a much wetter Mars, or a Mars that had a lot more water that was able to flow on the surface as in liquid form. This is a very exaggerated depiction. It probably didn't look like this, but it definitely had something in the past that it doesn't have today that allowed for it to have liquid water flowing on the surface. So my job is to try to understand what caused this change, as well as studying the water cycle as it evolved from the stage on the left to the stage on the right. So one question that we try to answer is, where did that water go? And really there's two directions. It could have escaped to space, or it could have gone into the planet, so up or down. And for escape to space, that could have happened via thermal escape, where you break down the H2O into hydrogen and oxygen, and then when it reaches the upper atmosphere, it can be stripped off by thermal escape, ion escape, which is driven by the solar activity, or it could have gone down to the crust, where it would have been incorporated into the minerals there by hydrating them. So for example, clay is an example of a hydrated mineral, and that is removing water from the atmosphere and from the system. You can have it be stored as underground water in salty, briny lakes. This is a hypothesis that was proposed, still not 100% proven. And then it can be stored as permafrost or in the ice caps. But essentially, this is another direction in which the water can go. I'm interested in looking at how the water cycle has changed on two timescales. So I'll be showing you in the rest of the slides two projects that I worked on, or one of them I'm working on, and one of them I've already worked on and has been published, alhamdulillah. The first one is a long-term effects or evolution of the water cycle. So how the water cycle has evolved on billion-year timescales. And the way that we can study that is using isotopic D/H analysis. And then later on, I'll switch to talking about my current research project that I'm working on to understand the seasonal and day-to-day changes of the water cycle and seeing how they exchange with the polar caps, which is one of the largest known reservoirs for water currently on Mars. And really, when you're trying to understand anything about water on Mars, you need to have these different approaches to try to build the entire story for how water has evolved. So starting with the long-term project, this is titled Evolution of the Water Budget Over 3.3 Billion Years. And the motivation for this, like I said, is to understand how the water budget evolved over billions of years and what we can learn from studying that evolution using the isotopic ratios. And the hypothesis that we put through and the results that we came up with is that the Martian water budget for the majority of Martian history was mainly controlled by escape to space, so that movement away from the atmosphere, away from the planet, and being outgassed from the interior. So outgassing just means when volcanic activity occurs, you're introducing gas that was locked up inside the Martian mantle back into the Martian system. So any volcanic activity that spews out gas is an outgassing event. And so the hypothesis that only escape to space and outgassing are really controlling how the water is evolving in this time scale. So I built a model, a very simple one-dimensional box model. And this is a depiction of what that model looked like. So on the left, you're seeing the main processes that are occurring, and all the water in the Martian atmosphere I am putting into an exchangeable reservoir. and allowing the process to proceed over time, where you're removing water to space via a specific escape mechanism that affects those isotopic ratios, and then you're introducing water into the system through outgassing, and that also affects the isotopic ratios in a specific way. And then I have constraints on those isotopic ratios from measurements that we've made. So on the left, you're looking at the starting position for my model, which is around 3.3 billion years ago. And the reason why we chose that is because we actually have a measurement. So the Curiosity rover was able to measure the D to H ratio in a parcel of clay that was dated to be 3.3 billion years old. And so that gives us a starting point for that isotopic ratio. And today we can measure the D to H ratio in the atmosphere and compare the two and allow the reservoir to evolve over time. And here's just a little simple depiction of why the D to H ratio will change over time and how we can use it to understand anything about the water. The connection is that water is stored mainly as H2O and as well as HDO, which is just deuterated water where the H is replaced by deuterium. And those photochemically can break up because of solar input. So the sun hits the water molecule, it can photochemically break it up into hydrogen and oxygen. That hydrogen can then be transported to the upper atmosphere, where when it reaches the exobase or the very edge of the atmosphere, if it has enough thermal energy, so just by its own inherent velocity, it can escape to space. But hydrogen and deuterium have different weights. And so deuterium is going to be more difficult to remove than hydrogen. And so over time, you're going to be preferentially removing more hydrogen than deuterium. And so you will enrich that D to H ratio, which is why you see it went from 3 times to 5 times the terrestrial value as we've measured it. So the results from this project are that essentially, if you have a water budget today that you measure to a high degree of accuracy, you can now use this model to go back and say how much water you started off with 3.3 billion years ago, and how much outgassing and volcanic activity that is associated with. So what you're looking at over here is the initial water budget on the y-axis and how much water remains today on the x-axis. And we aren't really sure how much water that is actually stored on Mars, because there are those subsurface reservoirs that are of unknown volume. So once we do get that refinement, you can go, for example, and say, yes, today we have 30-meter global equivalent layer of water, and that is associated with anything between 50 to 120 meters of water in the past. And if Mars did have 120 meters of water in the past, then that is associated with a very high outgassing rate. So there was a lot of volcanic activity happening during this time period. And if it was at 50 meters in the past, then that is associated with a history of Mars that didn't see a lot of volcanic activity. So this was the results from the first long-term evolution model. And currently, I'm working on looking at the short-scale evolution of the water cycle and what's going on right now as we observe it on Mars. And specifically, I want to understand the water cycle by observing ice clouds and snowfall. And I'm not talking about water snowfall as you would think of it here on Earth. On Mars, the dominant snowfall mechanism is actually CO2 snowfall. And the process of CO2 snowfall can affect the water snowfall. And I will explain it in the next few slides. But our hypothesis for this project is that water ice clouds and water ice particles are contributing significantly to the amount of water that is being exchanged in the poles, specifically through a mechanism called condensation, by acting as a condensation nucleus for CO2 and CO2 snowfall. So to describe what that mechanism looks like in images, you start off in the Martian polar region where it's cold enough that you have all the ice, all the water in ice form instead of gas form, because the temperature is really low, and so it goes from gas to solid. And then specifically in the winter, it gets even colder that CO2 can start going from gas to solid form. And it starts condensing on the water nucleus, because if you're familiar with how clouds form, you need a seed for the gas to start condensing on, and water, because it's already solidified, acts as the seed for CO2 ice. And then over time, you build up the CO2 ice on that water nucleus, and then it precipitates out onto the surface. And this is the process of snowfall, as you would know it, and deposits that CO2 and water onto the surface. So I'm trying in this project to understand how much water is being removed from the atmosphere during a winter season through this process. And before I dive into how I do that, I wanted to show you what the data I'm working with looks like. And this is a plot showing data from the Mars Climate Sounder, which is aboard the Mars Reconnaissance Orbiter that's currently orbiting Mars and studying its atmosphere. And this data is essentially just a compilation of multiple days that I put together and binned. And what you're looking at over here is the entire Martian atmosphere from the North Pole to the South Pole, so from minus 90 degrees to 90 degrees. And the center right here is the equator. And you're looking at the y-axis being the altitude. So as you go higher, this is the surface at the bottom, and then space somewhere up here. And the first of these is showing temperature information. The second is showing water ice particles. And the third, which isn't relevant to this research necessarily, but it's a pretty cool swath showing the dust data in the atmosphere. And I'm gonna play this now, and you're gonna watch it go from being southern winter to northern winter. So I hope you guys are able to see this progress through time. If you notice the temperature, right now it's northern winter above the North Pole, because there's a significant drop in the temperature, and it forms what is known as the polar vortex. So this little triangle over here is currently over the South Pole, and it will migrate to be over the North Pole. This is an area where there is a lot of cold air that is not being mixed with the rest of the atmosphere. And so there's a lot of cold air that allows water to condense out that you can clearly see in the water ice data. And it also keeps a lot of the dust outside of the northern polar region. So I am now going to talk about how I will be focusing on this specific area to understand how much snowfall is happening here and how much water is being removed from the system in specifically the winter region. So another plot that wasn't part of those is that you can get the CO2 ice density in that region. I've specifically zoomed in on the northern winter polar region. So now you're looking at 60 degrees to 90 degrees north in the winter. And this is just showing you the density of CO2 particles, and where there's a higher concentration, that shows us that there is a CO2 ice cloud over there. And I've extrapolated at the very bottom because our measurements can't go all the way to the surface. And so I had to essentially make an assumption of how the CO2 behaves towards the bottom. But I can now use this to track how the clouds evolve over time. And so clouds usually behave in a specific way. They follow specific physics rules. I will not go into the details of them due to time constraints, but you can find that over time, if you take an individual line from this plot, it will evolve in a very in a manner that we can model through our computers. And so this is a movie showing the evolution of a single cloud profile. So you start off with some specific number density where there is a lot of CO2 up in the upper parts of the atmosphere. And over time, as it is snowing down, that density will shift and the cloud will settle towards the surface and be snowed out. And there's also processes that are diffusing the CO2 up and down. So you get a dampening effect. And if you let this run its course, you'll find that over time, the CO2 cloud will have removed the majority of the carbon dioxide from the atmosphere. So, okay, I'm talking about carbon dioxide. What does this have to do with water? The connection here, as you may remember, is that this CO2 that's being removed from the system is also removing water from the system and adding it to the polar cap. And so you can now make assumptions on how much of the CO2 is actually condensing on water and on the different sizes of the particles. And eventually you can come up with something like this plot, which shows the same, plot that I showed you before, showing number density as a function of altitude and latitude. And you can now track how it evolves over time and how much water is being deposited on the surface for this specific region for just a 2-hour time band. So you start off with the clouds being higher up in the atmosphere, and then they slowly make their way down. And as they make their way down, you're snowing CO2 out and adding water to the surface. Now, there are gaps in the data. This is something that you'd have to work with and make sure that you're not incorporating any faulty data or removing anything that is inaccurate, but eventually you will get an amount of water that is being deposited on the surface, and you can study this evolution on longer timescales. And by longer, I mean multiple Mars years, and seeing how the water shifts from the north to the south. And this is where my project is right now, but hopefully the next steps is to expand this analysis to be over the entire Martian pole for an entire Martian year and multiple Martian years, and do comparisons. So yeah, that was a lot to talk about in just 15 minutes, but I hope that this was helpful information on just seeing where the water studies on Mars are at right now, and specifically how my research is helping with that. And I'll take any questions now. Thank you.
Thank you very much, Nora. Nora, I'm just going to ask you one question here before we dive into the question and answer from the audience. Why does Mars no longer have liquid water on the surface? What changed geologically?
So it's mostly the fact that you don't have a thick enough atmosphere for water to exist as liquid. So it's not about the fact that Mars lost water that you can't have liquid on the surface. It's because it lost its atmosphere. The atmosphere is the most significant part of maintaining liquid water on the surface. And so losing that water is really, losing that atmosphere through the process of atmospheric escape that is driven by the solar wind is what made the pressure get too low. And so you don't have enough pressure that is that will allow the water to be liquid on the surface.
Great, thank you very much, Nora. Just to inform everyone here who is attending this webinar, we might be just running a few minutes over time specified to close this webinar. So I'm just going to take a few questions from the Q&A, and for the any questions that I direct to a specific presenter, please make sure your answers are quite short, just for the sake of time, please. So we'll start off with Noor Al-Maheri. There's a question from John Paul that states, what is mock global map?
So it's basically is the wide-angle global map spot with images that are taken by Mars orbiter camera that is on board Mars Global Surveyor.
Thank you very much, Noura. And here's a few questions for you, Hassa, by Abdullah Al-Amri, that says, does the model only work for polar orbits? I believe he was referring to the model that you showcased in your presentation.
Thank you, Abdullah, for the question. And no, it doesn't work only for polar orbits. As we know, the Hope probe orbits wouldn't be polar, but we're using this analysis to predict what the instrument would give us.
Thank you, Hassan. The follow-up question is, how did you go about developing the imperial equations for the model with specific constants for corrections?
All right, so we did have a defined equation, but one of the things that I've done first is putting the equation for the code and for the model with free constants. So I accepted any kind of constant that the model had returned. So I didn't first force any kind of constants in there. And that was the second model. The first model that I've done that I've based it on our current understandings when it comes to the Martian atmosphere. So I've used the constant that we have in the literature and we plugged it there and we had a good consistency between both of them.
Thank you, Hassa. And just one more question from Krishna Prasad that mentions, was events like CME and SEP affecting the brightness observed?
The answer is yes. So that's one of the things that I had to deal with when I tried to pick the study areas. So I tried to pick data ranges that didn't have CME and SAP effects, but that wasn't possible all the time. So I tried to minimize that kind of effect in the data sets. So I had some of these events impacting the data and they would shoot the brightness up. So one of the things that I had to do is filter out any kind of outliers to the data to get it out of the correlation.
One last question for you, Hassa. Will the observations and conclusions from EMM help the research scientists develop a better Mars atmosphere model than the ones that are currently existing now?
That's very much true. The reason for that, the current models that we have about the Martian atmosphere depends on two things. One, our understandings of the physics of Mars, based on the observations that we have, and then the second based on the observed data sets that we have from different spacecrafts. And when it comes to the Martian atmosphere, the Hope probe does address shortcomings that we have when it comes to our understanding. So we don't yet have a full picture of the Martian atmosphere that covers daily data, seasonal information, and global coverage as well. So having all three available to us would definitely enhance our current understanding, thus the models that we have about the Martian atmosphere.
Thank you very much, Hassa. I'm going to ask just one question to Khalid. In terms of thermal contrast, what value is generally desired from what you've spoken about in your presentation?
So I generally go for values of 10 and above because we need a proper thermal contrast in order to obtain radiances of different constituents throughout the atmosphere. And usually the best time to obtain good thermal contrast is between 7 a.m. and 7 p.m. in Mars.
Thank you very much, Khalid. And one question for you, Fatma. How will you use your developed model after EMM science data arrives?
One of the ways that we're going to be using this model will be basically to compare the results that we get from Emirates Mars mission to the results that we got into the model, and will help us verify, cross-verify both the results from the model and also the results that the data that we will receive from EMUSE.
Thank you very much, Fatma. One last question for Hoor before we close the session. Can you talk more about the hydrogen escape?
Noura explained it very well, but hydrogen escapes through atmospheric stripping because of solar winds and because of thermal escape or Jeans escape when hydrogen reaches a velocity high enough to be able to detach itself from the Martian atmosphere.
Thank you very much, Hoor. So I went a little bit overboard with the timing of the webinar, and I hope that is okay. Apologize if I've used up a lot of time from the attendees here, but we tried to address all questions, whether it was through a typed response or by a live response, and I hope we managed to get most of the questions answered from you guys. So I would like to just mention one last thing for those of you who are interested to access the content that was presented here in this webinar. It was being recorded throughout the whole session, and the video will be up on the EMM website under the Hope Science Journey webinar series for you all to access. And to revisit the content that was being presented here. And that will be done within a few days, hopefully. So I would like to just take a moment to thank the presenters and all the attendees for joining this webinar as well. So thank you very much and enjoy the rest of your day.